Let's move on to question 1c. So referring to figure 2, calculate the current flowing through the 5 ohm resistor and the 4 ohm resistor. So we are given with this circuit over here, which consists of two power source, or you can say source of EMF. So one 12 volt, one 14 volt, and you have 4 resistance, which are labeled R1, R2, R3, and R4. So then they also label the current in some of the path. They label it as I1, I2, and I3. And now they're interested to find the current flowing through the 5 ohm resistor, which is the current flowing through this resistor, and the current flowing through the 4 ohm resistor, which is this resistor over here. So we see that there are more than two power source over here, or there are more than two source of EMF over here. So what we are going to do is we are going to use Kirchhoff law or Kirchhoff rules in order to solve this problem over here. Okay, so I'm not sure how to pronounce Kirchhoff. Like, I've searched through internet for its pronunciation and there's many versions, so just forgive me if I pronounce it wrong. If there's someone who can correct me, feel free to correct me. Okay, so we are going to use Kirchhoff rule to solve this problem over here. So Kirchhoff rule consists of two rules inside it, which is the junction rule and the loop rule. So we are going to go through the junction rule, then the loop rule for this circuit over here. But first, what you do is you should check that every single component in the circuit has already been labeled with a name. So what I'm trying to say here is, if you look at the two power source over here, we should see that it has been labeled with a name. In here, I label it as epsilon 1 and epsilon 2. Okay, since they are sources of EMF, right? Okay, then the four resistors over here are labeled with R1, R2, R3, and R4. So all the components have been given with a name. So we have done checking the components. Next, we look at whether the current flows in a logical direction or not. Okay, when I say whether it's logical or not, you have to look at the junction to see whether the junction has logical flow of current or not. So let's try to see what I'm trying to say here. So we have two junction over here, one above here, one below here. Okay, so when you look at the junction, you have to make sure that the flow of current is logic. Means by you cannot have current all flowing into the junction. Means that all three branch, they are all flowing into the junction. Because if they are all flowing into the junction, then the current flowing in, there's no way to go out, which is not logical. Okay, you cannot also have situation where you have current all flowing out from the junction, but nothing coming into the junction. That's also not logical as well, because that means where does the water come from? If all the water is flowing out, where is the water flowing in? There's no water flowing in, so that's not logical as well. So if you look at the junction over here, we have current I1 flowing into the junction, and we have current I2 and I3, which is flowing out from the junction over here. So this is a logical flow of current, because that means by I1 current flows in from here, then after that it splits into I2 and I3 into different branches over here. So everything is still logical. You have current flowing in, you have current flowing out from the junction. So if the current is logical, what can we do now is we can label more currents along the way, just to make sure we are able to see which resistor should be related to which current. Okay, so what I do is I'll label everything more times. So you have I2 over here, so passing through, then it will be I2. Okay, I hope this is logical to you. Like, unless you meet a junction, only your subscript will change. Okay, because when you meet a junction, only there's a way for you to branch out, or there's a way to combine the current. So unless you reach the junction, only you change the subscript, or else you keep the subscript. So in this case, there is no junction along this path from here to here to here, no junction, so all of them are I3. So from here to here, there's no junction as well, so I2. Okay, so I2 and I3 will combine into this branch over here. We see that before that, I2 and I3 originate from I1, because I1 breaks out into I2 and I3. So if I2 and I3 combine back, it should combine back into I1. So here is where you get your I1. So I1 is here. You can label more times, it's fine. Okay, if you are unable to see clearly, then you can feel free to draw more times. Okay, so you see everything is logical. This is I1, so the whole journey over here without any junction, this journey here, all of them are current I1. Okay, so once you have labeled everything clearly, you can proceed to do your junction rule and your loop rule. So we'll usually start with junction rule. I usually start with junction rule. So for junction rule, okay, junction rule says that the sum of I is equal to 0 at any junction. Okay, if the circuit diagram is logical, then sum of I should be equal to 0 at any junction. So let's pick one junction. We pick this junction over here. Okay, so when we say sum of I, what do? Is we take current flowing into the junction, means entering the junction. We call it a positive current, whereas current that is flowing out from the junction, we call it a negative current. Out means by getting less and less in the what we have at the junction will be less because it's flowing out, so it's a negative. So if it's flowing into, there will be more at the junction, so it's a plus. Okay, I hope you're able to get the idea. So into positive, out negative. So in this case, it will be positive I1, it will be negative I2, it will be negative I3, and they are all equals to 0. Okay, so you look at the junction, identify all the current, assign the correct sign in front of this current, then equals to 0. So that is what you do for junction rule. Okay, next you move on to loop rule. So for loop rule, you have to identify which loop you are going to analyze first. Okay, so loop is a closed path, means that if you start from this place, you have to find a path for you to get back to this place. So if you start from here, you move through this path, a loop will be something like this, going through this path, then coming back to the same position. So this is a loop. Or you can choose to start from here, then you can go through the bigger loop. You are still able to end back at your initial position. So this is also a loop as well. So this small rectangle here is a loop. This large rectangle here is also a loop. Then this small rectangle at this side is also a loop as well. So there are 3 loops. Feel free to choose any loop that you want to analyze, and feel free to choose any direction that you prefer. In this case, I have decided that I want loop A to start from here, then it will end back up at here, and I'm going to turn clockwise in my journey over here. Okay, so this is my starting point. I'm going to turn clockwise through this loop and end back at the original position. Okay, so loop rule tells us that the sum of V should be equal to 0 at any loop. Okay, so I've labeled this as loop A. So let's see, loop A, how do we build our equation? For loop A, I'm going to use a highlight pen to trace where am I currently. Okay, so I'm going to start from here. So my journey will be a clockwise journey. So I start from here. Then the first thing that I encounter will be a resistance. So there will be a change in potential, or there will be a potential difference when I cross the resistance 2 over here. Okay, so what will be the value of the potential difference? Well, it's, let me do this, sum of V for loop A is equal to 0. So because our highlight pen, my highlight pen here, it's following the direction of the current. Okay, my highlight pen is following the direction of current, therefore there will be a drop in potential. That's why it's negative I1 R2. Okay, this is the potential difference across R2. Okay, and as I say, we are going to sum up all the voltage throughout this loop over here. And this portion here is the potential difference across R2, and it's a drop. That's why it's a minus, because you give up energy to this resistor when you follow the direction of current. Okay, continue. So you continue your journey on this loop, and the next thing that you encounter will be second resistor, which is R3. So again, this time your highlight pen here, it's following a direction of current. I2 is going downward, and your highlight pen is also moving downward as well. So your loop is following the direction of current. Your highlight pen is following the direction of current. Therefore, you should expect another drop in potential. So this one will be negative I2 R3. Again, look carefully. What is the current passing through the resistor? I2. What is the resistor over here? R3. So it's negative I2 R3. Negative is because my highlight pen or my loop is following the direction of the current. Okay, so let's continue. So we continue our journey. Then the next thing that we encounter will be another resistor as well. This time is resistor 1. So this time we see that our highlight pen is again following the direction of current. The direction of I1 is the same as our direction of highlight pen or the direction of loop. So again, if it follows, it's another drop in your potential. So this one is I1 R1. Okay, so let's continue our journey. We will continue our journey, and the last thing that we will meet will be a source of EMF or a battery. So for a battery, we will use the EMF over here, but should it be a positive or should it be a negative? Well, in this situation here, your highlight pen is moving from the negative terminal to the positive terminal. Your highlight pen is moving from the negative terminal to the positive terminal. So if that is the case, you are having a potential gain. So that is positive epsilon 1. Why is it a potential gain? Because any charges moving outside the circuit for an external circuit, you lose energy. Then when it enters the battery from the negative terminal, the battery will supply energy to the charges to move to the positive terminal. Then only it can get out from the positive terminal full of energy, giving out to the external circuit and come back with zero energy. So at negative terminal, you have zero energy, then the battery will supply energy to the charge to bring it to a higher potential. So you should expect the journey to go from a negative terminal, which is a lower potential, 0, to a place, the positive terminal, which is high in potential, should cause you to have a gain in potential difference. So the gain in potential difference will be equals to epsilon 1, since there is no internal resistance for this case. So the whole journey, the potential difference will be positive epsilon 1, which is what I've written over here. Okay, so let's continue our journey. We'll continue our journey until we reach back to the same position where we start. So now we have closed up a complete loop. So we write equals to 0. This is what we do. Okay, so next, let's move on to loop B. Loop B, I have picked loop B to be the loop on the right, which is the rectangle shape on the right. So again, I'll start from this position over here, this junction over here. Then I'll move in a clockwise direction until I reach back to the same position. So over here, I'm going to use another color for my highlight pen. So I'm going to start my journey like this. And the first thing that I encounter will be resistor 4. So in this case, my highlight pen is going to the right and my current is flowing to the right. So my direction of my highlighter follows the direction of the current. So in this case, I should expect that it's a drop in potential once again. Okay, follow current, drop in potential, go against the current, rise in potential. So in this case, it's negative I3 R4. Okay, be very careful. This is resistor 4, but the current flowing through is I3. Okay, so let's continue our journey. We'll continue our journey until we reach this battery over here. But this time, our highlighter is moving from the positive terminal to the negative terminal. So if you follow what I discussed just now, the journey of a charge from the negative terminal to a positive terminal will be supplied energy by the battery. So you cause a gain in energy for the charge to move from a negative terminal to the positive terminal. But now it's happening in reverse. You're going from the positive terminal to the negative terminal. So the opposite of gaining energy is losing energy. Therefore, you should expect this is a negative epsilon 2. Okay, so for sources of EMF, if your highlighter goes from a negative terminal to the positive terminal, you gain energy. But if your highlighter goes from a positive terminal to the negative terminal, you are losing energy. Okay, of course, when I say highlighter, it's because I'm using a highlighter over here. You can feel free to just follow the loop over here. That's fine as well. Okay, so let's continue my journey. Then there's nothing here. There's nothing here as well. Then once I reach back to this center branch, I see another resistor. Okay, so this time I'm passing through the resistor, but as you can see, my highlighter is moving upwards, but the current I2 here is going downwards. So the direction of my highlighter is opposing the direction of current. So if that is the case, it should be a positive IR. It should be positive I2 R3. Again, why is it positive? Because just now we say if we follow the direction of current and pass through resistor, we give energy to the resistor. So if you look at it from a reverse direction, then you can consider a gain in energy. You look at it from a reverse direction, means by you reverse the direction of current. You look at it in the direction reversing the direction of current. I mean, you look in the direction that go oppose the direction of current. Okay, that's the way to say it. Okay, so now I'm looking in the direction that oppose the direction of current, so I should have a gain of potential difference. Okay, then now I continue my journey. Then I'll reach back to the point where I start. So once I reach back to the point where I start, I put equals to 0. Okay, so what I do now, I've completed the equation for junction rule, for loop rule, and for junction rule, loop rule for loop A, and loop rule for loop B. So what I do now is I substitute all the value that I have. Okay, what I don't have here is I1, I2, and I3. So here there's nothing that I can substitute. But I have the value of R2, R3, R1, and epsilon 1. I have the value for R4, R3, and epsilon 2. So let's substitute everything in. Okay, so this will be negative R2 will be 2, I1, negative R3 will be 6, I2, negative R1 will be, where's R1? 5, I1, plus epsilon 1 is 12. Okay, once I substitute it, I arrange it in this form. I1, I2, I3 equals to something. Okay, that's something I'm not sure yet. Equals to something. Okay, so if you look over here, I1, there's these two terms that involve I1. So negative 2, negative 5, so it will become negative 7 I1. So here I write negative 7 I1. Next, I look at I2, there's only one term here that has I2, so it's negative 6. For I3, if you look over here, there's nothing. None of the terms here involve I3, so there should be no I3 in this equation. So I write plus 0. Okay, then lastly, what should I have on the right? Well, there's only one number that does not have an unknown. So this number will be shifted to the right and it becomes negative 12. Okay, so this is how I shape my equation. Okay, let's look at loop B. Loop B, let's do our substitution. It will be negative R4. R4 is 4, I3. It will be negative epsilon 2, which is negative 14. And you have plus R3. R3 is 6, I2. And that will be equals to 0. Okay, now again, we arrange our equation in this form that has I1, I2, and I3, and it's equals to something. I1, there's no terms that involve I1, so there will be 0 I1. Next, for I2, there's only one term, so here is positive 6. For I3, there's only one term, so it's negative 4. Then what should you bring to the right? The only term without unknown is negative 14. Bring it to the right, it will be positive 14. Okay, so now you have constructed the equation for loop B. Okay, so right now the equation that you have, if I draw a line over here, you have three equations right now. The first one is I1 positive 1 I1 minus 1 I2 minus 1 I3 equals to 0. Then the second equation you have is negative 7 I1 negative 6 I2 plus 0 I3, and is equals to negative 12. And the last equation that you have is 0 I1 plus 6 I2 minus 4 I3, and is equals to 14. Okay, by this stage over here, there's a few ways you can solve the problem. You can do it the traditional way by solving it using simultaneous equation. So you can say I1 is equals to I2 plus I3. Then this I1 over here is substitute with I2 and I3. Then you try to manipulate the equation until you're left with 2 unknown. Then you further manipulate until you're left with 1 unknown. Then you do it using simultaneous equation. But here I'm not going to talk it using the traditional simultaneous way. I'm going to do it using another way. Okay, I'm going to solve this problem using something that you have learned in your maths class from semester 1. And I believe if I write it this way, you should be able to get what I'm trying to do here. Okay, I believe this bracket has been haunting you for semester 1. Come back again now. Okay, so what do? You bring in a number. Positive 1, negative 1, negative 1, negative 7, negative 6, 0, 0, positive 6, negative 4. Okay, so this one will be I1, I2, I3. Okay, then you have 0, negative 12, and 14. Well, it's just a matrices question actually. So your aim right here will be to find I1, I2, and I3. Well, if you do it in your semester 1 mathematics class, what you need to do is either ERO to find the ERO, elementary row operation, or you can do inverse matrix to find the inverse of these matrices first. Then after that, you multiply with this one. Okay, there are many ways to do it, but we are not going to do all that thing. What are we going to do is just key in into our calculator. Okay, so if you have your calculator, okay, in this case, this is a Casio calculator. What you can do is you can move to the 5th mode, which is on equation. I don't know whether the camera can catch it or not. But if you're on this calculator, you can press mode. Then move on to the 5th mode, which is equation, EQN. Press 5. Then after that, what you do is you select the second mode, which is ANX plus BNY plus CNZ equals to DN. So the second mode, you pick the second mode. Then now you end up with 4 times 3 matrices. So you have column A, B, C, D, and you have row 1, 2, 3. Okay, so what you need to do is you just key in based on your matrices. You key in this as A, B, C, and D. And this is 1, 2, 3. So what you need to do is just key in all these things. And once you press equal, you get the answer. Okay, so you can do it yourself. Key in everything into your calculator. Then once you press equal, you get the first answer, the second answer, and the third answer. Okay, you have to press equal a few more times to get the other answer. So I believe you get I1 to be equals to 0.38 ampere, I2 to be equals to 1.55 ampere, I3 to be equals to negative 1.17 ampere. Okay. Yep. Okay, so this is the answer that you can obtain. But if you look at the question asks for current flowing through the 5 ohm resistor and the 4 ohm resistor. The current flowing through the 5 ohm resistor will be I1. So you can write a label, something like that. Okay, you can say this is current flowing through 5 ohm resistor. Okay, how about the current flowing through the 4 ohm resistor? The 4 ohm resistor is over here. So 4 ohm resistor is over here. So what is the current flowing through it? I3. Okay, so you can label this one as current flowing through 4 ohm resistor. Okay, I'm sorry for the mismanagement of space. Okay, so this is how you obtain the answer to this question over here. If you look over here, there's a negative answer for I3. What does it mean over here is that the assumption that the current is flowing to the right, downwards, then to the left is actually incorrect. The correct or the actual direction of current is actually in the opposite direction to what we assume over here. So the actual correct direction, okay, you can redraw another new circuit diagram to show the new direction of current. The actual direction of current should be I3 pointing in this direction instead. Okay. So what happened if you look over here will be current flowing from the current flowing through from the positive terminal of the 12-volt battery, go until reach this junction, then flow downwards. At the same time, current flowing from the positive terminal of the 14-volt battery flow through R4 and come downwards. So the two branches over here, their current combine into R2, and once they reach here, they split again into I1 and I3. Okay, so that is what actually happens inside this circuit. Before that, we don't know, so we assume a direction. I1 is to the right over here, I3 is to the right over here, I2 is downward. But after going through the whole Kirchhoff rule, this whole calculation, we managed to figure out that what we assumed just now is actually incorrect. It should be I3 pointing to the left, so it should be flowing in this direction instead. Okay, so this is the ability of Kirchhoff rule in to help you understand or to help you determine the direction of current flowing in the circuit. Okay, so that's all for question 1c.